The index vector is a vector with all the loop index variables, with the outermost loop first. I mean the loop index variable of the outermost loop first. And then the index values are simply the values of these variables. And the index space of a loop is a subspace of Zm that consists of all the index values. Okay, now an affine array reference is an array reference where the expressions that compute the index are all linear functions of the loop index variables. If we require that, then it will be much easier to analyze the program. But there are cases that are also easy to analyze, even if they are not affine array references, such as this. And so what is this? Well, we have an unknown, or at least some variable that is part of the expression, but which we don't know the value of. And a technique called symbolic analysis can analyze these expressions to determine that there are really no data dependence between the iterations. As one can easily imagine, these expressions and symbolic analysis can become, from easy to too difficult. So here one can spend a lot of time improving symbolic analysis to make the compiler better. There is of course a limitation, because we don't want the compiler to take too much time to analyze the code. So there is a trade-off between how much time it takes and when it's no longer worthwhile. Okay, this particular loop comes from a collection from the Argonne National Laboratory in the United States, where they have collected source code that are in use at the various laboratories in the United States, and tested which commercial vectorizing compilers can handle them. So it's quite interesting. And lots of these loops are written without for, but instead with gotos. Okay, so some difficult non-affine index variables, index functions. If we read the variable and then use it as an index, then the compiler cannot know whether there is a data dependence or not. One option is to use runtime testing to see if X is within the loop bounds, and if it's not, then it can be ignored. An alternative is, if it is within the loop bounds, one can use two loops, so that in the first part, one splits the loops in two parts, one where X is outside the loop bound, and the other where it's, also outside the loop bound, but less than I. And then one iteration where I is equal to X. Okay, and another difficult is when we have indirect indirect references, so that we read a variable, an array, to determine which index we want to use. That is very difficult to analyze. And non-linear functions of the loop variables is also very difficult to analyze. So, how should we represent array references? It's the same idea as for the loop bounds. Namely, that we use matrices and one matrix per reference and a constant vector. So if this is the reference with different dimensions, then we can represent this as the matrix as shown here, namely the first here is the first column, etc. And the matrix is called the coefficient matrix, and the vector is the constant term. Okay, now well, now we have an example, and well, it just shows, so for instance 2 and 3, it's these two. Okay, so using matrices to represent them is quite natural and convenient, since now we may be able to create an equation that can be used to determine if there would be a data, I mean if there is a data dependence between iterations. And how can we create such an equation? If we have two references and they must be to the same matrix or vector, if they are to different matrices, or I mean to different variables, they are not the data dependencies, since obviously they are not writing or reading the same elements if they are to different variables. Okay, so the first check if they are to the same variable. And then what we really mean is that one of these two references, I mean this one is somewhere in the loop and this one is somewhere else in the loop, and at least one of them is in an assignment, I mean to the left hand side of an assignment. Then what it means that there is a data dependence is that these two different iterations both access the same array or matrix element. And in other words, that means that some loop index variables times the matrix plus this vector are equal to some other loop index variables, I mean in the same loop obviously, times this matrix plus this vector. If there is an integer solution to this, then there is possibly a data dependence. Okay, what we can do is to write it, I mean we just rewrite it like that, and then to avoid having two matrices, we actually write them like this instead. So we just create a new matrix with this one above minus b, and these two I and j, they are index variables, but since there are two different iterations, there will be I mean if we have a loop with I, j, k, there will be one I in this and one I in this and one j in this, and etc. So if there are if we have a three nested loop with I, j, k, then there will be 6 unknown variables. Okay, and we can write them like this, and then to simplify the notation, we can say that this vector that we want to find an integer solution to is, we can call it x, and just, well, not to, the purpose is not to confuse, but normally we write this new matrix as A as well. So we forget this A and that minus B and just write x equals, sorry, not equals, but okay, I write it like this. Oops. We set up the equation like this. X times A equals C. Okay, and that A is that A and above minus B. Okay, since now we can solve this, I mean without thinking about that they are loop iterations and actually consist of two different matrices. Okay, so we want to find an integer solution to this, so we solve linear Diophantine equations, but it's not certain that there actually is a data dependence even if we find an integer solution. And why? Well, I mentioned it before, namely if the solution is outside the loop bound, then we can ignore it. But if there is a solution within the loop bound, then we have data dependence.